Good evening, everyone. Welcome to O-Level Physics lesson. My name is Mr. Chu. Today is Tuesday, 8th of March, and we'll be on our second lesson on static electricity. Okay, so what we're going to do today is to finish up a brief overview of the topic of static electricity, and if there's time, I will also introduce a little bit of the next topic. Okay, which is current of electricity. Then next week, we will go through the O-level questions regarding static electricity. Okay, that will be the plan. Okay, but if any of you would like me to go through any revision or any past topic, please let me know. I will set aside a bit of time at the end to quickly revise. So if you have any requests. Okay, so meanwhile, I would like all of you to on your camera. Okay, Hao Rui, Ziying, can you please on your camera? Okay, so before I start, I have a check-in question. Okay, so let me share with you some of the things that we have gone through last week. Okay, so before I start, let me show you what I like to show you a lot, which is the mind map. Okay, those who are new, if you have never seen this before, you may want to take a screenshot. Okay, I find it very nice. But today I will not talk too much about this. Okay, so we are now at this part, static electricity. Okay, where my cursor is. Okay, the wave, thermal physics, and Newtonian mechanics we have all covered. If any one of you need extra help in the earlier topic, please let me know. I will try to help you. Okay, if not, the progress from now onwards will be static electricity, then current, then circuit, and so on. Okay, so this is the whole physics syllabus that you need to know for O-level physics. Okay, so those who are interested in this, have you taken a screenshot? Okay, so once you are done with this, I'll close this and I will go through the syllabus again. Okay, I mentioned this last week. Okay, just briefly explain again. Electricity and magnetism are linked. Okay, but in the earlier part of this topic, of this theme, we call this the themes or section V or theme 5. Okay, we'll study electricity first, then we'll study magnetism. Then the last two topics, we will study how electricity and magnetism are related. Okay, the last two topics, we are using electricity to produce magnetism. And the last topic is using magnetism to produce electricity. Okay, so that is what we're going to do, okay, for the last two topics. Okay, and these two concepts are linked together. Okay, so what we have done last week, we talked about static electricity. Okay, just let me go through what is important, and meanwhile, if you can, please write down notes. Okay, first of all, for electricity, okay, all of you need to know that there are positive and negative charges. Okay, there are positive and negative charges. Okay, so this is similar to magnetism. Magnetism, there are north and south pole. Okay, I'm trying to link you with another topic which you haven't learned yet, but you have learned north and south pole in primary school. Okay, so it's very similar with magnetism. Electricity actually have two charges, okay, positive and negative. And then the charge is measured in Coulomb. Is that clear? Okay, so let me add on a bit of things here. Let me add on. Why Ryan come in again? Okay, so let me add on. The symbol for charge is Q. Okay, the symbol for charge is Q, and the symbol for Coulomb is capital C. Okay, so my second question that I asked all of you, what is a Coulomb? Okay, Coulomb is a measure of the number of charge. Is that clear? It's a measure of how many positive or negative charges has moved past. Okay, so for example, if I have a pipe, This is a pipe. Okay, and in electricity, it is not the positive charge that move, it is the negative charge that move. So let me talk about charges that move. So for example, there are charges moving through, all the negative charges, we call them electron. Okay, you learned this in chemistry before. Okay, so what does Coulomb mean? So 1 Coulomb, okay, 1 Coulomb actually means a certain number of negative charges that you see. Okay, the number of negative charges that you see. And that number is a very big number. I can't remember the number. If I'm not wrong, it's 6 times 10 the power of, is it 18 or 23? Okay, let me Google the answer. Who remember the answer? How big is 1 Coulomb? Okay, one of you mentioned just now. Let me see what is the value. Okay, Yuting mentioned to me is okay, wait, Yuting, your answer is so small. Okay, so 1 Coulomb is 6 times 10 the power of 18. Okay, 18 charges. Okay, it can be positive charge or negative charge. Okay, so for Yuting, it is 10 about 18. Okay, you're not wrong. 6.24 is more accurate. Okay, but the power is very important. It's actually 6 million number of electrons. Is that clear? So when you add them together, if you have 6 million electrons, that is 1 Coulomb. Okay, that's a lot of charges. Okay, so we actually measure the number of charges in Coulomb, and the actual definition of Coulomb or charge is the actual definition is the amount of charge, okay, that 1 ampere of current will flow in 1 second. I repeat myself again. Charge is the number of charges is equal to the amount, okay, is equal to 1 ampere of current. Okay, sorry, let me repeat. Sorry. So in primary school, you have learned current and voltage. So if I tell you that the current is 1 ampere. Okay, I represent current. So what does 1 ampere mean? 1 ampere means there are 1 Coulomb of charges going through that point every second. I repeat myself again. 1 ampere means there are 1 Coulomb of charges flowing through that point every second. Okay, so I will lead you to the formula that I introduced last week, and this formula will be seen in the next chapter. Okay, so I already mentioned current is the amount of charges that travel through the point every second. So you use that definition. Literally, you can say that the formula is I equal to Q over T. So current is the amount of charge that is the rate of the amount of charge that is flowing. Okay, why are we not using this formula in this topic? Because in this topic, we are talking about static electricity. Okay, we're talking about charges that do not move. Okay, so this formula will only be introduced at the next topic where we talk about charges that move. How many of you are with me so far, or how many of you are already confused? If you are with me, give me a yes reaction. If you're confused, give me a no reaction. Okay, I talk about this a little bit because it's linked to the next topic. Okay, so if the charges are not moving, okay, if the charges are not moving, okay, we actually use Coulomb to measure charge, and then 1 Coulomb means there are 6 times 10 about 18 charges. Okay, that's all you need to know for this topic. I just link it to the definition about moving charges. Okay, so to introduce to your for the next topic. Okay, next thing. Unlike charges attract and like charges repel. Very similar formula. Very similar law with the law of magnetism. Okay, law of magnetism is the same thing. Unlike poles attract and like poles repel. So for magnet, okay, instead of charges, we change to the word poles. Instead of charges, we change to the word pole. So the concept is the same. If you have unlike things, unlike charges or unlike poles, they will attract. Just like male and female will attract. Correct? Whereas if you are two guys together or two girls together, by right, you should repel. Okay, so this law is similar to human. Okay, boy like girl, girl like boy. Okay, so unlike charges will attract, like charges repel. So you cannot remember this law, just remember about the relationship of most people. Okay, most of us are straight. Okay, boy will like girl, girl like boy, correct or not? But boy and boy will not like each other. Okay, romantically. Okay, so it's a similar type of concept. Okay, next thing. I also talk about the field. Okay, field-wise, there are three types of field that all of you need to know. Okay, let me share with you what the three field. We talk a lot about magnetic field. Okay, and then the last one we need to talk about is the gravitational. Okay, these three, when you see the word field, you can interchange these three words together. So what you need to do is just to interchange the electric to magnetic or gravitational. So for electric charge, okay, for electric field is electric charge. For magnetic field, it will be a pole or magnetic pole. Okay, and then for gravitational field, we use a mass. Okay, so all these actually just interchange and the whole thing has the same definition. So let me repeat myself. Electric field is a region where an electric charge experiences a force. Okay, so a magnetic field is also a region where a magnetic pole experiences a force. Okay, the force is a magnetic force. The first force is the electric force. Is that clear? The last one, a gravitational field is a region where a mass experiences a force. And this force is a gravitational force. Okay, so why am I saying this is I don't want you to remember three separate things. Okay, just want you to remember one thing that can apply to three different parts of physics. Okay, and they are similar. Clear? Okay, so this is what we have gone through last week. So this week, you're going to go through something that is more difficult. Okay, let me show you some notes. Okay, I'm going to show you something that's more difficult, which is the principle of electrostatics. And I remember when I was a student, it confuses me a lot. Okay, hopefully I can make things easier for you. Okay, so before we continue, last week we talked about insulators. So a lot of electrostatics or static electricity is got to do with insulator. Okay, why? Because insulator do not conduct electricity as they don't have a free electron. Whereas conductor, electrical conductor or thermal conductors, they can conduct heat or electricity just because they have a free electrons. Okay, so electrical insulator don't have all these three things. Okay, so therefore, when you see in an object, the electrons are not free flowing. Yes, the electron may not get stuck to the atom by itself. Okay, but unlike matters, the electron can actually freely flow throughout the material. Am I right? Whereas for insulator, both the positive proton and the negative electrons are not able to move about freely. Okay, are not able to move about freely within the material, and therefore is not able to conduct electricity easily. Okay, whereas for electrical conductor, it can conduct electricity because the negative electrons can easily be moved throughout the material. Clear so far? Okay, so let me just revise this example again. How do I make the glass and the silk charge? So starting off, they are both neutral. Okay, why? Can you see over here? Glass rod has 5 positive and 5 negative at first. Then the silk also have 5 positive and 5 negative at first. So both of them are neutral. Okay, the second concept you must know is this. We have learned before, positive charges are proton. Okay, are proton. Can proton move? Can proton move from one particle, one material to another material? Okay, it cannot. The proton and the neutron forms the nucleus that makes up part of the material. Okay, so proton does not actually move. So anything that moves will be the electron. Okay, I want you to remember this. Okay, between proton and electron, things that move will be the electron. The proton will stay put with the material. So what makes the material positive or negative is basically a lack of electron or a surplus of electron. Did I make myself clear? Okay, so at first they are neutral. They are both positive and negative, positive and negative. Then what you're going to do is you use the silk to rub the glass rod. When you rub, what happened? I told you already, the positive don't move. So for the glass rod, the positive don't move. For the silk, the positive also do not move. Okay, because they are proton, they stay with the material. So the positive positive charges, which is the proton, stay with the material. Whereas for electrons, they are small enough to be displaced, but because they are insulator, you cannot move the electrons freely. But when you rub enough, some electron can still be moved. Okay, some electron can still be moved. So in this example, when you use the silk to rub the glass rod, 3 of the electrons jump over. Okay, jump over. So you end up with 2 negative, and then you got 8 negative on the right side. Okay, so can you see? 3 of the electron actually jump, okay, from the glass rod to the silk. Okay, so eventually when you rub enough, the glass rod will have 2, you will only left with 2 electrons, whereas the silk will have 8 electrons. 1, 2, 3, 4, 5. Okay, sorry. This electron is here. Can you see these 3 electrons? Now they are moving, and now they got extra 3 here. Okay, so at the end, the silk has 5 positive and 8 negative. Then how do we tell which one is a positive material and which one is a negative material? So look at the glass rod. The glass rod has 5 positive and 2 negative, so it's net. The net is 3 positive. Therefore, the glass rod become a positive. Whereas the silk has 3 extra negative, and therefore the silk become negative. Okay, that is how you can make an insulator positively charged or negatively charged. Okay, this concept, is that clear? Okay, the concept is the proton cannot move. It is the electron that move. So how does the electron move? You actually use friction, and then you rub the material together, and then some of the electron actually jump from one to the other, and it makes one of the material positively charged because of lack of electrons, and the other material negatively charged because of extra electrons. Okay, this idea, as a student, I'm always confused. I hope all of you understand. If you understand this idea, give me a yes reaction. If you understand this, give me a yes reaction. If you are confused, give me a no reaction. Ryan, why you never put your name, your index number, sorry, in your Zoom name? Okay, so this is what we covered last week. So this week, we're going to talk about the principle of electrostatics, okay, which I don't really like as a student, but as a teacher, I will want to explain to you clearly. Okay, so let's look at this. How am I going to make object actually positively charged or negatively charged? Okay, so for this principle of electrostatic, okay, previously we talked about insulator. On top, we talked about insulator. Now we are talking about metasphere, and these are all conductors. So it's a bit different from the one above. So conductors, your electron can freely move. Okay, your proton, same thing, cannot move. Okay, but your electron can move very freely. Whereas for insulator, the proton cannot move, but the electron also cannot move, but some can still move. But for metal conductors, sorry, electrical conductors, the electrons can actually move freely. Is that clear? Okay, so what is going to happen here is there's a few things that we are doing here. First, we have these two. Okay, can all of you? Okay, maybe all of you take 2 minutes. Read through the step 1, 2, 3, 4, and then you tell me whether you understand. Okay, can all of you clear your yes and no reaction? Then if you finish reading, if you understand what's happening here, give me a yes reaction. If you don't understand at all, give me a no reaction. Okay, so I want you to read the 4 steps and tell me, do you actually understand what's happening? As a student, I don't understand. Okay, so it's okay not to understand. That's where I'm here to help you. Okay, Hao Rui, Ryan, and Chelsea have read this and understand. How about the rest of you? Thank you, Yufan. Ziying, Oscar, Yuting, are you okay? Thank you, Oscar. Yuting, don't understand. Oh, okay. Ziying, how about you? You have learned this topic. You totally understand what's happening here, or you need more help? Okay. So all of you have learned this topic in school. So all of you understand except for Yuting, because Yuting haven't learned this. So spare me some time. Okay, so Yuting. So at first, the A and B, the sphere are metal. Okay, so the electron can freely move if you actually connect electricity to these two spheres. But down here, there's no electricity. So the electron by right will not move. So even for metals, it can be neutral. Okay, so the plus, minus can be all neutral. So at first, there's nothing disturbing the two spheres. So the two spheres are neutral. Is that clear? But because they are both touching each other, can I treat this as one whole thing? One whole thing where they are both neutral. Okay, can I treat these two circles as one whole object? Okay, one whole object. The positive cannot move, whereas the negative can move around if you want to let them move. Okay, but because there's nothing to disturb them, they are neutral. Okay, next, I bring a negatively charged rod. Okay, but I don't touch it. So remember the concept. The concept here is unlike charges attract. Okay, so if this thing that I bring, this rod, I bring near the left side, because unlike charges attract, okay, what happened here is this. Remember I told you there are 2 plus and 2 minus on the left side and 2 plus and 2 minus on the right side. If I were to bring a negative rod near this, the positive will move. The positive will not move. Is that clear? Okay, the positive will not move. It's only the negative that's moving. So when I bring it close, because of unlike charges attract as well as like charges repel. Okay, this principle you learn that. What happened is the negative and negative will repel. the positive by right should attract, but because the plus cannot move, and you're holding on to these two things. So the plus will not move, the negative here will not move, okay, but this negative at A will actually move because the negative, the electron, can move freely. Okay, so these two negative will have a repulsion reaction, and these two negative will end up going to the right side. Is that clear? So on the right side, there'll be more negative. On the left side, there'll be more positive. Okay, but the positive did not move. Is the reason why the left side is more positive because the electrons in A repel with the electron in the rod, and the electron can freely move. They all run to B. Okay, Yiting, are you clear about this? Okay, Yiting, if you understand, give me a thumbs up. Okay, very good. Thank you, Oscar. Okay, everybody remove your reaction. Okay, so now when you have this rod close to A, and A and B are still touching each other, while still close to A, you split the A and B apart. You split the A and B apart while the rod is still near A. Okay, while the rod is still near A. So what happened here is the negative from A already jumped to B. Okay, the negative from A already jumped to B. So the B itself has more negative, the A has less negative, therefore it becomes positive. Okay, it has become more positive, and that's what happens when you split it apart. Then the last step is you remove the rod. This rod is the thing that caused the negative to jump to right side, right? Then you remove the rod, everything will actually try to balance again. Because there is the lack of electron, the left side will be a net positive sphere, and the right side will be a net negative sphere. Okay, so this is one way to charge two metal sphere to make one sphere positive and one sphere negative. Okay, the word we call induction is because there is no direct contact. We are trying to put it close to it. Okay, and then it influences the electron to jump. Okay, so we use induction because there's no direct touching between the rod and the sphere. Okay, and therefore the word here is induction. Is that clear? It is indirect. Okay, so it's called induction. Okay, so that is how we can actually make two metal sphere, which is one that is slightly positive and one that is slightly negative. The whole process here, all of you understand clearly the concept? So the main concept is this. Proton doesn't move, number one. Number two, you need to understand unlike charges attract. So okay, never mind. Unlike charges not very important. So the two main concepts you need to know is this. Number one, protons don't move. And then number two, like charges repel, or unlike charges attract. So if I were to bring a negative thing here, the negative and the negative will repel. If I were to bring positive, instead of negative, they're all positive, okay? So positive and negative should attract. So unlike charges attract, the electron will now jump the other way around. Did I make myself clear? Okay, this part, if you totally understand, give me a clap. Okay, give me a thumbs up. Oscar, why are you trying to sweep me away, huh? Ryan and Ziying, are you okay with this? Charging two metal sphere by induction. Okay, next. Now, what's happening here? Another example, charging a single metal conductor by induction. Okay, in this case, we previously is two metal conductor. Now we change to single metal conductor. Okay, using the same concept. Okay, the same concept, the same two principles. Number one, proton don't move or electron move. Okay, only electron move. And number two, like charges repel and unlike charges attract. Okay, based on these two principles, take about 1-2 minutes, read this 4 steps. If you totally understand, give me a yes reaction. If you are confused, give me a no reaction. Okay, Chelsea and Yuting understand now, so I will not go through too much. Okay, Ziying, Ryan, and Yufan, any question for me? Okay, Yufan, which step are you confused? 1, 2, 3, or 4? Okay, Ziying, which step are you confused? 1, 2, 3, or 4?
Step 2, like what happens if you earth it at the negative charge end?
Okay. Okay, Yuting, you asked me a question just now. You say that there are still protons in B, just that B is more negative after induction. Okay, let me go through Yuting's question first. Okay, yes, there are still negative. There are still proton in B, just that there are extra 3 electrons, so therefore it becomes more negative. Okay, whereas for A, the A doesn't mean there's no electron, just that we lost 3 electrons, so become slightly more positive. Okay, you think understand now? Okay, some of you are confused step 2. Okay, let me look at step 1 first. Okay, in this case, you are supposed to bring a positively charged glass rod near a metal conductor. Okay, first step, very simple. What happens is you put a positive here, and because it's positive, and then the proton don't move, so the proton still remain there. Clear? The proton remain there. Okay, at first, maybe there are 4 proton and 4 electron. Okay, so what happened here is when you put a positive charge on the left side, you attract. Okay, first of all, proton doesn't move, so the plus don't move. Okay, and then you put a positive charge here, so positive charge you only and then we only consider the negative, the electron. So how is electron and positive will react? They are unlike charges, so they will attract. Okay, they attract. So these 2 negative will go to the left side. Is that clear? So these 2 negative go to the left side, end up on the left will be slightly, you have more excess of electron, and on the right side, there will be lack of electron. Okay, so on the left will be negatively charged, and then on the right will be positively charged. Clear so far? Okay, so when you do that, okay, after you put the positive charge near this thing called, not the sphere, this one is called the metal conductor. On the left, we have a bit more electron because it's attracted by the positive. On the right, you'll be more positive because some of the electron has gone to the left side. Okay, so then what happened next? While putting the rod still on the left side, okay, still on the left side, what happened is you put your hand acts as a ground. Okay, your hand acts as earth. Okay, this is the earth symbol. Your hand acts as a earth symbol. Okay, so what happened here? Okay, your ground itself, your ground or the earth has unlimited electrons. I repeat myself again. Earth has unlimited electron. It can supply unlimited electron, or it can actually absorb unlimited electron. I repeat myself again. Earth has an unlimited supply of electrons. Either you can supply the electron or you can absorb all the electrons. Okay, so on the left side, okay, now we actually see, we break into two here. They are not broken, but because of the presence of the positive charge on the left side of this metal conductor will still have a bit of, it'll be still negatively charged. Okay, because of the presence of the plus on the left side. So there'll be more electron on the left side. Then, when you put your finger on touching the right side, I told you already just now, your earth acts as a unlimited supply or absorption of electron. And then things always like to be neutral. So on the right side here, okay, there is a lack of electron. So in this example, the earth will supply the electron to neutralize the right side. Okay, it neutralizes the right side. Is that clear? Okay, so by touching on the right side, you are actually connecting the earth to the right side using your hand, and then you whatever electron that is missing here will be supplied by the earth. So the right side become neutral. Okay, so the 4 plus is still there, right? But then this 4 neutral, this 4 negative comes from the hand. Okay, so on the right side, because the number of plus and minus are the same, the right side is neutral. Is that clear? All this while with the plus still on the left side. Then what happens next is you're going to remove this plus away. And as I told you earlier, at step 2, the earth will want things to be as neutral as possible. Okay, so when the left side is negative, the right side is neutral, what happens? You'll try to balance, you'll try to find an equilibrium point. So these 4 extra electrons will now spread out throughout the metal conductor. Clear? So this 4 is on the left side because it's attracted by this positive charge. When I remove this positive charge, this excess 4 negative charges will now be evenly spread out throughout the whole thing. So that is how you make one metal conductor charge up. Okay, did I make myself clear? Okay, can you all clear your reaction? If you understand, give me a tap. You don't understand, give me a no reaction. Yifan, you okay? Okay, so I do not wish that you all memorize all these steps. All I need you all to do is to remember that proton don't move. Okay, like charges repel, unlike charges attract. And then the new point here is you must know that Earth is a supply or absorber of electron. Okay, so this is the 3 things that you all just need to remember, and then you can apply all the way. Okay, you first ask me a question. So the hand in contact with the positive side will take away the positive charges into the earth. Okay, no. Remember, Evan? Okay, Evan, can you repeat the statement and share with everybody? Okay, share everybody. Then I'll explain to you. Okay, the positive does not move. The proton does not move. Yes. So when we put our finger, okay, let me talk in simple terms, not in electron and proton. We talk in simple terms, when your hand acts as earth touch something, that thing will become neutral. So it seems like the positive disappear. Okay, that is how it seems to happen. Okay, but in actual fact, because proton doesn't move and electron can move, when you touch the finger there, Yes, you're not wrong to say that the positive all go away. But you must also remember the proton doesn't move, so the positive still stay there. So how do I make the positive go away? Is to make them all neutral. To make them neutral, I need to introduce electron. So for every extra positive, I need to have extra negative. Okay, so the Earth supply the electron to neutralize every single positive here. So when you neutralize it, the plus seems to disappear, even though the protons are all still there. Okay, Ivan, you understand my explanation now, or you are still confused? Okay, so you cannot say that the positive are taken away. The positive are okay. To say like that is not wrong, but what is actually happening is not the positive charges that is taken away into the Earth. Okay, what you say is not wrong, calculation-wise is correct. Okay, but the actual thing that's happening is the electron that comes up. Then the positive no longer become positive. Okay, you find understand now? All right. Okay, great. Okay, let's talk about the next one. How do I discharge a charged insulator? Okay, in this case, we're talking about insulator, not conductor. And remember, the difference between insulator and a conductor is, for insulator, the electrons cannot freely move. They can still move, but they cannot freely move like a conductor. Yes, over? Okay, so for example, you have a glass. Glass is an insulator, and you happen to make it a positively charged glass rod. Means that some of the electrons are taken away. Okay, so therefore the whole glass is positive. It's not because you add plus into the glass. The glass happen to be positive because by friction, you are able to strip off some of the electron. Electron can be removed and added. Okay, in an insulator, not freely. In a conductor, it can move freely. In an insulator, electrons cannot be moved freely, but it can still be removed and added. Clear? Okay, so for this case, the positive charge rod is brought near a flame, okay, a Bunsen burner providing a flame. The intense heat actually will ionize the air particles around it. And these ions, okay, the ionized air, so the air is ionized, so air split into positive ion and negative ion. Okay, and all these ions itself will neutralize the excess charges on the glass, and then the glass will become discharged. It becomes neutral. Okay, so what happens is some of the negative will join in, and then you'll neutralize the whole thing. So you can use heat to neutralize a charged insulator. Okay, the word we call here is discharge. Another way to do it is to put the charged insulator in a humid condition. So this example is where the balloon become negatively charged. On the left side is the glass rod is positively charged. So to become positively charged, you take away some electron. Then for a balloon to be negatively charged, you add some electron. How do you add? You rub it by friction. Okay, you add by friction, and then it becomes negatively charged. Then the water molecule in the air are electrical conductors. How many of you believe this statement? How many of you believe that water molecules in air are electrical conductors? Isn't water a non-metal? Okay, so in the environment where it's very humid, where there's a lot of water molecules, this water molecule actually will absorb or actually supply excess charges to make your insulator neutral again. Okay, the key word here is discharging the charges. Clear? And why are some water a conductor of electricity? It's not because that water is a metal, but when water mixed with some impurities or some ions, okay, it becomes electrically conductor. Okay, so basically, the two main way of discharging a charged insulator is by heating things up, or you put the thing in a humid condition where there's a lot of water particles in the air. Okay, next, discharging a charged conductor. Okay, I mentioned about this earlier. So basically, to discharge a metal charged conductor, okay, the keyword here is conductor. We use earth. Okay, we use earth. Okay, conductor are usually metal. Okay, we use earth. So, for example, if this sphere has too many electrons, it is negatively charged. To make it neutral, you must take away the extra electron. So by touching it, the extra electron will go to earth and the whole thing become neutral. Okay, so far? Likewise, when the sphere is positively charged, it means that there's lack of electron. There's too many protons, the electron being taken away. So to actually make the metal, positively charged metal neutral, you need to discharge it. How? Same thing, just provide earth to the metal sphere. Okay, so earth will either supply the electron to neutralize it, or you will actually absorb the extra electron to neutralize it. Okay, so from charged conductor is very simple. You just need to earth it. Once you earth the thing, it will become neutral. Is that clear? So for this part, if you understand how to discharge both a charged insulator as well as a charged conductor, if you understand perfectly, give me a thumbs up. Thank you, Yiting, Oscar, and Ryan. How about the rest? Chelsea, thank you. Thank you, Yifan. Ziying. Okay, so far up to here, this charging, discharging, the proton don't move, electron don't, actually can move, has always been confusing to me as a student. But for you as a student, after learning in school, for most of you, plus additional explanation from me, is this concept very clear to all of you now? Can? And then I do not want you to memorize the process. I just want you to understand the concept. Okay, in all of these examples, the positive don't move, only the negative move. And how does the negative move? Either by like charges repel, or unlike charges attract, or when there's a contact between conductors, then you move, or you actually connect to earth, then the earth will supply or absorb the excess electrons. Okay, just need to remember all these concepts. You can tackle all these examples. Okay, so I do not expect all of you to memorize all these steps, but I want you to understand the concept, then you can actually apply all these concepts to all the examples. Okay, is it useful so far? Okay, then now we go through, okay, basically today is the main thing that I want to go through, all this charging and discharging. Okay, this is the thing that is the hardest for this topic. Then the last part is about electric field. Okay, electric field. So we have learned forces in Newtonian physics. Force is a push or a pull. Do you remember? Okay, so if it's attracting each other, it is a pull. If it's repulsing each other, it is a push. Okay, so a force is a push or a pull. Okay, but why is it electric force? Because the push and the push come about when electric charges exert on each other. Okay, so when you put electric charges near each other, you will have a force. Okay, and the force is either attractive, which is a pull, or repulsive, which is a push. Okay, and then earlier on, we talked about the electric field. Okay, electric field is a region where an electrical charge experiences an electric force. Clear so far? Okay, region means the place or the space. Okay, a space where you put a positive electric charge. When you put the positive charge there, and it actually move in that direction, so that is the electric field. Clear so far? All these line that you see, the individual line you see, is called the electric field line. No need to remember. Okay, but all the lines drawn together, the pattern that you see is the electric field. Okay, so what's happening here is, if I were to put a positive charge here, okay, if I were to put a positive charge here, you will actually have a electric force in the direction of the field line. So this positive charge will go this way. Understand so far? Likewise, down here, if I put an electric charge, a positive charge here, it will move this way. Does it make sense? Okay, so the field line predicts how a positive charge will move. Okay, you'll predict how a positive charge will move. Okay, so if I don't have the electric, if I don't have the electric field line, you remember, if I put two positive together, it will repel, so it actually will move away. So it's actually still true. It still follow the law. Okay, likewise here, if I got one positive here and one negative here, they are unlike charges, it should attract. So it should move towards the negative. So you see the field line show this arrow. Okay, is actually predicting the way the positive charge will move. Understand so far? Okay. Okay, so how do we draw an electric field line? Number one. Okay, number one, last week I mentioned this. Positive will always have lines that comes out. Can you see? Positive always have lines that comes out. Negative always have line that goes in. So in O-level physics, all of you are expected to draw, okay, to draw the field line due to one charge. Okay, so in this case, if I just draw one positive charge, all of you are expected to be able to draw all the line going out like this. Okay, if I give you a negative charge, all of you are also expected to draw all the lines going in. Okay, so all of you are expected to be able to draw the positive charge line and the negative charge line. Next thing, all of you are also expected to draw the field line if you have 2 points. So the third example is this: when you have two positive together, like charges. This is how the pattern, the electric field pattern looks like. Okay? And all of you know, if I put 2 plus together, okay, we put 2 plus together, 2 plus mean like charges. So like charges will repel. Okay, all of you know like charge repel. So the field line that you see here, when you draw something like this, from the pattern that you draw, you should be able to see that these 2 plus will actually move away. Can you see from all this pattern that you draw? Okay, so if I have more lines coming out, can you see if I have one more line coming out here, you will actually go on top here. You'll go on top here. And the field line will never cross each other. So can you see? They will never join. So from the pattern that you see here, you can predict these 2 plus will repel each other and then go, will repel from each other. Understand so far? Okay, let me show you the one below first. What if we have like charges? Remember just now I told you, like charges attract. But let's say you don't know this. Let's say you don't know this. Your electric field will your electric field lines will be able to show that this is true. Okay, this is true. Okay, so if I have a plus and minus, remember I told you for plus the line come out. For minus the line go in. So for plus, can you see all the arrow is going out? And then for minus, all the arrow is coming in. So the only logical way to combine the arrows will be in this pattern. Clear so far? This pattern is the electric field lines for unlike charges. Okay, the other thing you need to also know is that if the lines are close to each other, can you see here? The distance between each line is very small. Can you see? Whereas the distance between these two lines are very far. If it's far, it is weaker. If it's closer, it is stronger. Can you see that? So can you see? Here and here is very close, so it is stronger. Compared to here is further away, so this way, this part is weaker, this part is stronger. Okay, so this is what you all need to do. Okay, this is what you need to know for electric field lines. Okay, let's go back to here. So can you see? When the lines are very close, it's actually very strong. So this is the part where they repel. Okay, where they repel. Whereas when they are very far apart, this is actually weak. Okay, so when the field lines are close together, it is stronger. If it's far apart, it is weaker. So can you see over here? In between is equal strength. But here it is further apart. So here is weaker. Here is equal strength, equally strong. Understand so far? Okay, so now we have gone through single plus, how it looks like. We've gone through single minus, how it looks like. We talk about 2 plus or 2 minus, how it looks like. Okay, so 2 minus will do the same thing, just that the arrow is the opposite direction. I repeat myself again. You have 2 negative charges. The pattern is exactly the same, just that the arrow is all going into it. Okay, all going in. Then we have also gone through 1 plus and 1 minus. Okay, 1 point, 1 positive point, and 1 negative point. And this is how it looks like, something like a magnet. Have you all learned a magnet before? If you have a magnet where there's North Pole and South Pole. So North Pole is like your positive. Okay, your line is going out. South Pole is like negative, where your line is coming in. Okay, so the pattern that you see here is very similar to a magnet. In fact, it's the same. It's the same pattern as your magnet. Sorry, it's this way. Okay, it's the same pattern as your magnet. Can you see? So if I were to draw a magnetic field, I compare it with an electric field, the pattern is the same. Exactly the same. Where the line is further apart, is weaker. Where the line are nearer to each other, they are stronger. So can you see when it's very, very near, it's very strong. When it's further away, it's very far. And the other thing that you also need to know is the electric field line cannot cross each other. So in your school, in your exam, in your higher learning drawing, remember if I draw properly, don't draw like me, like not very nice. Okay, remember you cannot cross each other. Okay, the lines, we cannot cross each other. Okay, so having said all this, you have learned it today here. Okay, you learned it today here. And when we go to the magnetic topic, same thing. If I have a North Pole here, you have the same drawing. If I have a South Pole here, I have the same drawing. If I have 2 North Pole here, it'll be the same drawing. You have a North Pole here and South Pole here, you'll have the same drawing as well. Okay, we have the same drawing as well. So I just want to tie in and link everything together. If it's positive of north, arrow comes out. If it's negative or south, arrow comes in. Is that clear? Okay, up to here, you understand? Give me a yes reaction. Wow, Oscar clap. Hey, after saying you change to thumbs up. Ryan and Ziying, are you okay? Did I actually help to make you understand better? Okay, so all the the point sources, I already explained. So we talk about plates, but it's no longer a point charge. Now it's actually a plate, okay, like this. So like this, same thing. Plus will still go to minus. Any lines that come out of plus, okay, any line come out of plus will be arrow go out. Any line go into minus will be arrow going in. Yeah, of course, you can still continue drawing. You can still draw like this. Come out, come out. Okay, no problem. It's still going out. Okay, same thing is still going in. Okay, it's still going in like this. Okay, you can extend the line. But the important thing is between these two, how the lines look like So you can predict what happened here. And can you see from here? They are like joining from one point to the other. This kind of pattern, does it look like they're going to come together or are you going to move apart? So can you all type it out? Type it out to me. When you look at this kind of pattern, does it look like attraction or repulsion? Okay, can you type? Okay, Yuting, you can see, well done. Ryan, correct, very good. So from this pattern, you can see that these two will have an attractive force to each other. Okay, just from the pattern, not because you know that unlike charges attract. Okay, Xiao Xing, well done. Where are the rest of you? Ziying, are you okay? Okay, so I expect to see you type attract or repel. Only 3% has given me the answer and they are all correct. How about the other 4 of you? Yifen, Hao Rui, Ziying, and Oscar. Okay, from this pattern that you see here, does it look like these two are going to come together or going to move further apart? Okay, Hao Rui, well done. Ziying, you okay or not? Are you there? Oscar, okay, Ziying, well done. Oscar, are you there? Yufen, are you okay? Yufen, I saw your answer. Okay, well done. Okay, one more thing I want to touch on before I continue. If you look at all these patterns, if I were to put a plus anywhere, you always move somewhere. Okay, I put a plus anywhere in all these 4 patterns. Okay, let me move out a bit. In all these 4 patterns, the field line will show you that where it's going to move. Okay, hold for a while. Okay, sorry, I have a call. Okay, so if I were to put a plus anywhere, the field line will actually predict how the plus charge will move. Okay, in this case, you'll move towards here. So anywhere I put a plus here, you'll show me that you go in this way. Okay, I put a plus here, you'll go this way. Understand? So so all these field line predicts how a positive charge will move. Okay, but among these 4 drawings, there's one point where when you put a plus there, it will not move. Okay, that point is called the neutral point. Okay, so let me show you this point. This point right here, right in the middle here is your neutral point. If I were to put a plus exactly in the middle, okay, between these two, the plus will not move. You can understand why, right? Okay, I can put a plus here, you'll move this way. If I put a plus here, you'll move this way. Okay, but exactly at the middle here, okay, you will not move at all. In fact, along this straight line, if I put a plus, okay, if I put a side on top, you actually will still move upwards. Okay, right in the middle, you will not move. So this point at the middle is called the neutral point. Understand? Okay, any question for me? Now let's look at the last few parts before we end today's lesson. Okay, an electroscope. Okay, electroscope is an instrument that detects the presence of electric charges. Okay, and this figure shows you the structure of an electroscope. So there's a brass cap on top. There's the brass rod in the middle. There's a gold leaf between here. Okay, there's a gold leaf. And these 3 items, the brass cap, the brass rod, and the gold leaf, they are all conductors. Okay, so in an uncharged electroscope, when it's not charged, the gold leaf will be both straight. Clear? Okay, because there's no attraction, there's no repulsion. They are both pointing down because of gravity. Okay, they are not reacting to each other. However, for example, if I were to put a positive charge rod near the top, you remember if I put positive charge rod, it will actually attract the electron going up. Okay, so what happened here? The two electrons below will go up. Therefore, on top, you'll be negatively charged. So on top will be negatively charged due to the induction by the glass rod. And then the bottom will be positively charged. And do you remember when they are all positively charged, they are all of the same charge, like charges repel, the gold leaf will actually move apart. You actually diverge. Are you able to explain this now? Are you clear about this? Okay, if you're clear about this, give me a yes reaction. Okay, if you are clear, give me a yes reaction. Okay. Then another example. If I were to put a negative charge rod on top here, I put it near the brass cap. Remember, the plus doesn't move. The plus doesn't move. The negative will move. So negative and negative will repel. So these two negative will flow down. So what happened is on top become positive, below become negative. And because the gold leaf, there are two of them, two negative gold leaf, what happened? It will diverge again. Is that clear? Okay, so when the gold leaf repel, it means that this item is charged. Okay, so regardless whether is it positively charged or negatively charged, when you see a gold leaf diverge, it means that the thing that you're putting close to the brass cap is a charged particle or a charged object. Does that make sense to you? Okay, now having said this, does this instrument, this electroscope, able to tell whether the thing that you're testing, is it positive or negative? Okay, tell me, type out in the chat, yes or no. Okay, having said this, having understand the concept, can this electroscope tells me whether the thing you're testing is a positively charged material or a negatively charged material? Yiting, well done. How about the rest of you? Can you tell? Ziying and Ryan, can you explain to me how you tell? Because I already give two examples. The positive example, you open. The negative example, you open. So how does, when you see both open, how do you know that the thing you're testing, is it positive or negative? So my question is, can this instrument test whether the thing you're testing, whether is it positive or negative? So what do you mean by glass rod? I don't understand. Can you type out a bit? Or you want to use the mic to explain? Okay, so for this example, okay, Ziying say something. The charged glass rod, this one, like whether you're using positive, negative. Okay, the thing that we are testing, here is this blue thing. Sorry, not this red. The thing that we are testing here is this rod or this rod. Okay, this rod, this rod. Okay, so does this instrument tells me whether this rod is positive or negative? Okay, so from what we see here, we will not be able to tell. Okay, the only thing an electroscope can tell is whether the thing that we are testing is charged or not. That's all. It will not be able to tell us whether is it positive or negative. Clear? Okay, if you understand this so far, give me a thumbs up. If you don't understand, give me a no reaction. Ziying, you okay? Okay, everybody clear your reaction. Okay, one more thing I want to share with you about this picture is, can you see what's the purpose of this earth here for? There is an earth here. What is this thing for? Can you tell me what, can you make a guess? What's the purpose of earthing the whole thing? Why do you want to put the earth there? Yu Fen says clear charge. Clear charge of where? Okay, so what's the purpose of why do we earth the metal case? Why do we want to earth the metal case? Okay, the keyword here is this is a metal case. So why do we need to earth the metal case? Any one of you have any idea? If you have no idea, type no idea. Okay, Ziying, well done. You got it correct. How about the rest of you? Do you have any idea why we put the earth there? Qiao Xing, well done. Yu Ting, your explanation is not clear enough. Okay, so basically I earth the metal case because I want my metal case to be neutral. Because over time, metal as a conductor of electricity, it can accumulate charge. Okay, whether extra negative charge or extra positive charge. Okay, so when you earth it, you make sure that your metal case will always be neutral. And when it's neutral, it will not affect the brass and the gold. Is that clear? So when your metal is neutral, okay, if it's not neutral, definitely it will affect the brass and the gold. Okay, so you want to make sure that the only thing that you're testing is the glass rod or the thing on top here, and it's not affected by the case. So you actually need to earth the case itself. Is that clear? All right. Very good. So all of you roughly understand what the earthing actually means. Okay, we have two last page, which is the application, and then we'll end the lesson today. Okay, so what are the usage or the danger of static electricity? Okay, lightning is an example of a static electricity. Okay, so I want you to read the 5 points here. Once you read finish, you give me a yes reaction. Okay, I don't want to read out loud to you. Okay, so once you read finish, take about 2 minutes, read about the lightning. Let me see any keywords I want to explain to you. Once you understand, give me a yes reaction. If you read finish, don't understand, give me a no reaction. Okay. All right, Chelsea and Ryan has finished reading. Okay, all understand. Ethan, are you okay? All right, so let me just quickly summarize. What happened is when thunder clouds because of friction between the water molecules in the thunder cloud and air particles. Okay, so the bottom of the cloud is negatively charged, and as I mentioned, plus doesn't move, proton doesn't move. So the negative charge at the bottom of the ground will go away. So negative charge will go away. So only then it becomes slightly positive charge. Okay, then when the negative charge on top become very high, what happens is the air around it will become ionized. Okay, and then there's suddenly between the cloud and the ground, there's a path. Okay, the path that is actually caused by the ionized air. And why the air will ionize? Because there's suddenly a lot of negative charges at the bottom of the cloud. Okay, so the ionized air, once it forms a path to the ground, okay, all the excess electrons from the top will all move to the ground. Then when you see a light itself, the path where the light moves is where the electrons from the cloud go all the way to the ground, and that is where lightning is formed. Clear? Okay, so that is how lightning is formed. Okay, next thing, electrostatic discharge. Have you seen before some cars are like big lorry, okay, on the road? Okay, the car itself on the road, they actually put a metal chain, okay, touching the body of the car to the ground. Maybe a chain, some chain. So this chain will actually drag along the road. So why do you want to introduce this thing to increase friction? Okay, because without the metal chain, the tire is made of rubber. Okay, a tire is made of rubber. Okay, so it's not made of metal. So as the car moves from a long journey, there's friction between the road and the tire. Okay, and this can actually accumulate charges on the vehicle itself. Okay, because remember I told you, to actually make an insulator charge, you can do it by friction. So as the rubber move along the road over a long distance, it can make the car electrically charged. And suddenly, what happens is if a sudden discharge occurs, means that let's say the car itself have a lot of negative, for example, a lot of negative, and suddenly there's all these negative discharge go to the ground suddenly at one time. It may cause a spark, and if your lorry is carrying things like fuel, the spark and the fuel can cause an explosion. Is that clear? So the key thing is how do we actually minimize all these charges from accumulating? Okay, how do we actually remove, okay, to prevent the charges from accumulating to a high enough level where it will cause a spark? So you don't want it to accumulate until so high where spark can occur. So what you do is you actually put a chain, a metal chain at the back of the vehicle or at the front, okay, and then it touch the ground. So the ground acts as the earth. Remember, the earth provides unlimited electrons, or it actually absorb unlimited electrons. So your car itself is always in constant touch with Earth, and your vehicle will never accumulate charges, and therefore spark will not occur, and the whole car will become safer. So you understand now why some people, you see some vehicles, you see all this chain touching the ground. It's so as to protect the car. Is that clear? Okay, if you understand this explanation, give me a thumbs up. Okay, another thing, this one, electrostatic precipitators. Okay, what exactly are these? Okay, so this thing itself is something like a filter. Okay, like ash filter. You don't want this filter to be in the air to pollute the air. So for example, the ash particle actually going through these filters, and this is a charged particle. On the left side is positively charged. On the right side is negatively charged. If I were to draw the field line, it will look like this. Do you remember? Okay, there is a electric field line. It looks like this. Okay, so what happens is when you burn something, or when there is actually some combustion that takes place, there will be gases and ash that will be going up let's say a chimney. And you don't want this chimney, okay, you don't want this gas to actually pollute the air. So one way to do is to install an electrostatic precipitator, where you have two charge plates. On the left side is positive charge, on the other side is negatively charged. So what happens is this, you have also a negatively charged wire on the way. So as the ash go through the negatively charged fine wire, the ash itself will also become negatively charged. Okay, so it becomes negatively charged. So as it goes up, the ash becomes negatively charged. So where will it move? Okay, I'm sorry. Both of these, okay, sorry, my drawing is wrong. It doesn't describe the same thing. Okay, both of these plates are positively charged. Okay, so as the ash go upwards, touching the negatively charged wire, okay, the ash will become negatively charged, and as it goes up the chimney, you'll be attracted to both the positively charged plate, and that is how you actually filter the ash from this chimney. Okay, so that the ash are collected by the plates and is not go up into the air. Okay, so this is one example of how an electrostatic precipitator works. Okay, so the first one, lightning, is hazard. Okay, the second one, this metal chain, is a application. Okay, electrostatic precipitator is also another application that will remove ash from the chimney. Okay, last one, there is a photocopier. How does a photocopier work? A photocopier actually make use of static electricity to work. Okay, this is the last part today. I will let you all read 1 to 9. Okay, if you understand, you give me a thumbs up. Then I'll give you a question. Yeah, you answer my question, you may go. So the earlier question will be faster. So you read the 1 to 9. If you understand properly, give me a thumbs up. If you don't understand, give me a no reaction. Or you give me a thumbs up, ask you a question, you answer me, you can go. Okay, Ryan, what is a photoconductor? Yiting asked me a question. Why is there friction? You're asking this question for which part? Sorry, I didn't see your question now. Okay, Qiao Xing. Okay, I will answer that in a while. Let me go through the photocopier first. Okay, Chelsea, my question for you is, let me think of a question first. Name me one hazard of static electricity. Okay, Yifan, can you tell me how quickly in one sentence how a electrostatic precipitator works? Okay, Chelsea, you got no other question, you may leave. Oscar, what is what is an electric field? Well, Oscar, how you know that's the question I asked you? Okay, Oscar, you may go. Ryan, can you read number 1? The answer is at number 1. A photoconductor, the answer for that is number 1. Okay, Ziying, you stay back for a while and talk to you. Hao Rui, what's the meaning of 1 Coulomb? Okay, Yifan, you understand, right? You know, if you have no question, you may go. Okay, everybody understand the whole idea about photocopier? Okay, all understand, huh? So I'm going to end the lesson now. If anybody got any question, you may leave. Okay, thank you, Ryan. You may go. Okay, thank you, everyone.